Good afternoon, class. I'm here to talk about astrophysics. There's a lot of things covering astrophysics, but you only have to know one thing. Excuse me. What are you doing here? Excuse me. This is a topic about Petrinets. Bioinformatics. This is not your class. Sorry, I thought this is about astrophysics. I didn't know it was a bioinformatics class.
Sorry about the disturbance.
I have to go now. Sorry, shall we start talking about Petrinets? Good day, this is your host, DARYL APOSTOL, and I'm gonna give you a brief background what Petrinet is. My topic is the overview of Petrinets. Petrinets according to bioinformatics. To start off, I'm gonna tell you the creator and founder of Petrinets. His name is Carl Adrian Petri. That is where the Petrinets came from his last name. And this was the subject of his dissertation in 1962. This introduction of Petrinets deals with the graphical aspect of Petrinets. As a beginner, you will find it hard using the mathematical construction of it from algebraic principles and all of those stuff. As a beginner, we will be making this topic easier by constructing it graphically. Well, Petrinets have been used all around the world, from office automation, workflows, and flexible maneuvering. Now, the basics of Petrinets. A Petrinet is a collection of directed arcs, connecting places and transitions. Extensions. There are many extensions in Petrinets. Some of them are completely backwards compatible. Now, with the original Petrinet, some add properties that cannot be modeled in the original Petrinet formalism. Although backwards compatible models do not extend the computational power of Petrinets, they may have more succinct representations and may be more convenient for modeling. Extensions that cannot be transformed into Petrinets are sometimes very powerful, but usually lack the full range of mathematical tools available. What we want in Petrinets is to represent it in a mathematical probation. In that way, students or teachers can understand it easily through graphical representation. Mathematical tools are least available on these extensions. We need these mathematical extensions in order to analyze ordinary Petrinets. I would be ending my report here. All of the other members will discuss how the Petrinet works and all of those other things. My topic is about the overview of Petrinets and the basics of Petrinets. Thank you for watching. I'm your host, DARYL APOSTOL, signing out. Thank you.
So, in detail, the general net theory is founded on the following axioms. First, the empty set is not a net relevant to theorem proving. Second, S and T are separate sets. Third, there are no... In detail, the general net theory is founded on the following axioms. First, that empty set is not a net relevant to theorem proving. Second, S and T are separate sets. Third, there are no isolated elements in a net. And the fourth, there are no short circuits, both forward and backward arrows between two elements. So, an event is a set of concurrently executable transitions. And the first is every net can be marked so that the class E of events is not empty. And the second, transitions in the same event have non-overlapping sets of connected state.
Abstract bioinformatics is a rapidly developing discipline that takes advantage of mathematics and computer technology to construct and analyze biological models. Petrinets are efficient tools used in bioinformatics recently, while their application needs to be further expanded. The survey which this paper provides of the application of Petrinets in bioinformatics study includes 3 parts. First is using place or transition system to qualitatively analyze structural properties of biological objects, using stochastic Petrinets to add stochastic properties to biological modeling and analysis, and last is using hybrid Petrinets to represent and analyze biological systems with both discrete and continuous properties. Finally, the application of Petrinets in bioinformatics is summarized in the research directions and open.
Hi, I'm FANCISCO, and I'm here to discuss about some representative examples of some Petrinets. Here are some basic examples: the simple reaction, the reversible reaction, and the hierarchical rotation reaction. Let's discuss furthermore about the reversibility reaction. Here you can see the figure. It is a figure to illustrate the general behavioral properties, where in the place A is 0 bounded, then the place B is 1 bounded, and the other places are 2 bounded. So the net altogether is 2 bounded. The transition R1 and R2, as you can see here, is the leftmost cycle are dead at the initial marking. The transitions R8 and R9, they're at this part. In the rightmost cycle are live. All other transitions are not live. So the net is weakly live. And also you can see the net is not reversible in this part because there's no counter reaction to the token decrease by firing of R4. And that's it.
Good day, I'm AMMUYUTAN and I'm going to report about Petrinets and how it's done. Petrinets consists of 3 types of components: places, or denoted by circles; transitions, or denoted by rectangles; and arcs, or represented by arrows. This is a sample net. Places represent possible states of the system. Arcs simply connects a place with a transition, or a transition with a place. And change of state is denoted by a movement of tokens or black dots from places to places and is caused by the firing of the A transition. The firing represents an occurrence of the event or an action taken. Places have infinite capacity by default, and transitions have no capacity and cannot store tokens at all, with the rule that arcs can only connect from places to transitions and vice versa. We have all we need to begin with Petrinets.